In this demonstration, we're going to see how we can estimate model parameters using measured data. We have a model of a hydraulic actuation system. When we simulate the model with these inputs, these are the results that we get. However, data from a hardware prototype looks like this. We can see that our model does not match reality. It is likely because there are parameters of our system that are not correctly entered into our model. We may not have that data from the datasheet, or they may have become altered over time. We could tune these parameters by hand, but a more efficient way would be to use optimization algorithms to tune them automatically. Using optimization algorithms, we can automatically tune these parameters until the results of the simulation match the measured data. Here are the steps that we'll go through. First, we will import the measured data. We will then identify the parameters we wish to tune and their ranges. Next, we will estimate the parameters. I will now switch over to the model so you can see how this is done. Here is our model of a hydraulic actuation system. A hydraulic valve controls the flow of pressure from a pump to a hydraulic cylinder. This input signal controls the movement of the spool. When we run the simulation, we will see how it performs. On this scope, we see the input signal, and on this scope, we see the position of the piston. The yellow line are the results of the simulation, and the pink line are results from a hardware prototype brought into our model here. We can see that they do not match. We need to adjust parameters in our model to make it realistic. The parameters that we are unsure of have been defined as MATLAB variables. We will automatically tune these variables to make the results match. To do this, we will use Simulink Design Optimization. I will click on this link, and this will open the Simulink Design Optimization tool. The steps that we need to perform are: first, we need to import the measured data. Here you can see the position of the piston that we measured from the hardware prototype and our input signal. The next thing we need to do is to select the parameters and their ranges. Simulink Design Optimization has detected the MATLAB variables in our system, and here we have specified the valid ranges for these variables. Again, we can't let the piston area go negative. That wouldn't be physically realistic. Now that we have done these two steps, we can now estimate the parameters. During the estimation, Simulink Design Optimization will automatically run the simulation, compare the results of the simulation with the measured data, detect the sensitivity of the parameters to changes, and then rerun the simulation. With each test, changes are being made to those values that are hopefully bringing it closer to the values and minimizing that cost function. You can see that each of these iterations are being done automatically, so even if I knew exactly the set of variables that I wanted to test, I couldn't enter them in manually and run the test as quickly as this is going. The other aspect of this is that because Simulink Design Optimization can detect the sensitivity of the results to the different parameters, it will be able to make a much better guess and estimate as to what the values should be than I would be able to do simply by looking at the plots. Even after a short period of time, we can see that the results of the simulation are much closer to the measured data. We could speed this process up even further by running the simulations in parallel. It is currently configured to run them sequentially or one after another so that you can see the individual iterations. However, it would be possible to configure this entire estimation to run in parallel, and that would accelerate the entire process. I'm going to stop the estimation now because you can see that the results are quite close. But if we did let it continue, it would continue to minimize that cost function until these traces were as close as possible. In this demonstration, we have seen how we can use optimization algorithms to automatically estimate model parameters.